All right, let's have a look at how we divide polynomials. Basically, it's the long division equation. You might remember this from primary school days, good old long division, where any number you could write it as the product of two numbers plus maybe some remainder. Well, it's still the same idea, but we're dealing with polynomials rather than numbers. So we call AX the divisor, what we're dividing by. QX is the quotient, so that's the answer when we do the division. But of course, we might have a remainder. Now, the degree of the remainder always has to be less than the degree of the divisor. Because if it's not, you can keep dividing. So once that degree is less than, you can stop dividing. And, oh, well, I suppose this one's a little bit trivial, but the quotient and the remainder are unique. So in other words, they must be different. Because if they were the same, well, then you could factorise the Rx and you wouldn't have a remainder. Here's an HSC question, 1998. We have to find the quotient and the remainder when the polynomial is divided. So we set up our division. So x squared plus 1 is going to go into x to the power 4 minus x squared plus 1. But the thing we need to remember with polynomials is, if you think of them like columns, you need a column for each of the powers. So I need to put one in there for the naught x cubed and the naught x as well. And when you're dividing, it's really just the leading terms you're dividing. So leading term into the leading term. So x squared into x to the power of 4, of course, goes x squared times. And then we multiply out. So x squared times x squared, x to the 4, 1 times x squared. So again, we get naught x cubed and subtract. So we get minus x squared, so that's minus 2x squared. Bring down the other terms. Now, the degree of my remainder is the same as the degree of my divisor, so I keep going. All right, x squared into minus 2x squared is minus 2. Multiply out, subtract, and I get 3. Well, the degree of 3 is less than the degree of the divisor, so that's our remainder. That's where we stop. So the question was, find the quotient and the remainder. Well, the quotient ended up being x squared minus 2, and the remainder ended up being 3. I guess what this means is we could rewrite this polynomial as x squared plus 1 times x squared minus 2, but then we'd have a plus 3. We've got the remainder. Okay. Wow, 1988. So this time, let's do it again. We're going to divide the polynomial. Okay, same idea. 2x squared, multiply out, subtract. So now x squared into minus 4x cubed. Oh, sorry, bring down the 2x minus 3. Minus 4x, multiply out, subtract. No, we can keep going, so bring down the minus 3 there. X squared into minus 2x squared, minus 2. Multiply out, subtract, and that's where we stop. Hence right, which is the logical thing to do, I guess. So there we go. We know it's our quotient with it times our divisor with our remainder. Now, the polynomial division is useful when we're looking at graphing as well. Because if we look at our division, polynomial x divided by ax, when we talk about fractions, when we rewrite it, it would be the quotient, because that's the division that works, but then we've got a remainder. So it's plus remainder x on divisor x. Okay. Same as if you were saying, oh no, let's think of a simple one with numbers. 2 into 5. How many times does 2 go into 5?
Twice.
With? Right. But the answer, if I said 5 divided by 2 is 2.5. So 2 is the answer, plus remainder 1 over divisor, 2.5. So it's the same idea. Now, why that's useful is because when it's written in this form, it tells us a lot about the graph. Because as we know, the bottom of the fraction can't equal 0. That'll work out the vertical asymptotes. QX turns out to be the horizontal or the oblique asymptote. Horizontal if it's a constant, oblique if it turns out to be a linear function, and theoretically you could have a quadratic asymptote and so on, but telling us what happens out at infinity. The top of the fraction tells us whether or not it cuts those asymptotes. Now, it can never cut a vertical asymptote, but it is allowed to cut a horizontal or an oblique one. And so if you solve the top of the fraction equaling 0, you'll find the place where it cuts the actual asymptote. So if I want to sketch x plus, so I've already got it in that format, x plus 8x on x squared minus 9. All right? Well, vertical asymptotes, bottom of the fraction can't equal 0. So we've got plus or minus 3. So let's put that in. Okay, oblique asymptote, y equals x. Pop that in. Top of the fraction here. Yeah, it is possible for that to equal 0. So I know that at the origin, it will cut that oblique asymptote. So, there. In fact, that's what it then ends up looking. Now, I can tell that straight away because, let's just go back to the equation. If I was to find x-intercepts and y-intercepts, then I could do that. Well, y-intercepts obviously is easy. It turns out to be 0. Well, we kind of knew that already because we knew it went through 0, 0. But if I was to put that all together as one fraction so I could find the x-intercepts, top of the fraction, we'd find that the only x-intercept was in fact x equals 0 for that particular one. So because that is the only x-intercept, then I know what the curve's got to do, because we know we've got to bend towards the asymptotes. So up here in the triangle on the right-hand side, I must bend like that. I can't go like that because there's no other x-intercept. So same with the triangle over here. I know it goes through 0, 0 and it bends towards the asymptotes. So the only question then is it the way I've got it here or is it flipped the other way? Well, it's easy enough to substitute a number in to work out whether it's positive or whether it's negative at that particular point.
It couldn't be the other way anyway.
Why could it not be the other way?
Because that's how the line is.
Oh, good point. Yeah, if it was the other way, we'd end up cutting that one again. And we know it only cuts at one spot. Well spotted. 4C.